Okay, let's just dive right into this explainer. Today, we're unpacking the chapter by taking these abstract geometric rules and, well, actually grounding them in the real world. It's kind of like a magnificent journey, going from simple, flat 2D patterns all the way up to complex, universe building 3D forms. Let's get into it. Here's a quick roadmap for today. We're going to build our understanding step by step. So we'll hit weaving, the rules of tessellation, classifying quadrilaterals, tangram puzzles, and finally jumping into 3D shapes. Section 1. Patterns in Weaving. So you've probably seen woven baskets just like this one around your house, right? But if you really stop and look closely at the surface, you'll spot these distinct mathematical patterns hiding in plain sight. I mean, way before humans were writing down complex equations, they were already using these highly structured geometric designs just to keep their everyday items strong and intact. Let's actually reverse engineer this. Imagine taking a simple piece of paper, cutting some vertical slits, leaving just a little gap at the top, and then getting 8 separate, colorful paper strips ready to weave right through it. Imagine doing this with your own hands. You take that first colored strip and weave it across those slits, one under, one over, one under. Okay, simple enough. But then, for the second row, you grab your next color and do the exact opposite sequence. And boom, this perfectly illustrates how just alternating your strips creates this highly structured, repeating visual layout. By literally just flipping your starting move on each row, you generate this beautifully tight matrix. It's simple, but it works so incredibly well. The absolutely crucial takeaway here is that a pattern is just predictable repetition. Whether row 1 goes 1 under, 1 over, or row 3 is 2 under, 1 over, that predictable repetition is literally the bedrock of the geometry we're exploring in this chapter. Moving on to Section 2, the rules of tessellation. Now, tessellation sounds like a massive, intimidating word, but honestly, it just means fitting shapes perfectly together around a single point. No empty space, zero overlapping. Think of it exactly like a perfectly solved jigsaw puzzle, but made entirely out of the exact same geometric piece. Before I show you the answer, test this out in your head. Picture grabbing a bunch of 5-sided shapes, regular pentagons, and placing them edge to edge. Do they fit perfectly around a single point? Well, if you take regular pentagons, where all 5 sides are exactly the same length, and you try to wedge 3 of them around a point, you're going to hit a massive geometric roadblock. Look at that annoying little empty space right there. Even though they are perfectly regular, symmetrical shapes, pentagons just cannot fill a flat region without leaving a gap. So by the strict rules of math, regular pentagons absolutely do not tessellate. Luckily, not all shapes are quite so stubborn. Equilateral triangles, squares, and regular hexagons fit together flawlessly. I mean, there's a reason you see hexagons in bee honeycombs. It's literally mathematically proven to be the most efficient shape to store the maximum amount of honey while using the absolute least amount of wax. Nature already figured the math out for us. Section 3. Classifying quadrilaterals. Let's look at 4-sided shapes. Notice the precise contrast here between these two. A kite has equal adjacent sides, meaning the sides that literally touch each other at a corner are the exact same length. A parallelogram, on the other hand, relies on equal opposite sides, so the lines running across from one another are equal, kind of like train tracks. Now, what happens if you take that parallelogram and force all its angles to be exactly equal right angles? You get a shape we all know and love, the rectangle. A rectangle is really just a super specialized parallelogram where opposite sides are equal and every single corner is locked in at a perfect 90 degrees. Section 4. Tangram puzzle. Let's put everything we've covered in the chapter so far to the test. Imagine taking a shape, say a rhombus, and shattering it into smaller triangles. How many completely different shapes do you think you could build from just 3 triangular pieces? Could you make a massive new triangle? A quadrilateral? The whole magic of geometry, especially with tangram sets, is seeing how these basic building blocks can recombine into an infinite variety of larger forms. And finally, Section 5, jumping into 3D shapes. Let's take all these flat 2D concepts from the chapter, the lines, the angles, the shapes, and literally pull them up into 3 dimensions. When flat shapes are combined the right way, they fold up to create solid 3D forms. Take a basic cube. It's really just 6 flat squares, but when you connect them, suddenly you have a form with faces, vertices, which are the corner points, and edges where those faces meet.
And this exact same framework helps us tackle the incredibly complex 3D models from the chapter, like the 20-faced icosahedron or the 12-faced dodecahedron. It's like a giant puzzle. You start asking, how many faces look identical? How many faces meet at one specific vertex? By breaking these massive complex models down into simple edges, faces, and vertices, we can literally decode the geometry of the universe itself.
So, as we wrap up this explainer, I have a challenge for you. Take a second and just look around the room you're in right now. Your desk, your walls, your screen. Can you reverse engineer the math that brought those everyday objects from flat, repeating patterns into their final 3D form? We literally live our entire lives inside mathematical equations. So what hidden pattern are you going to notice next?